Okay, so let's look at the details of how these things happen by using the water tank experiment. Okay, so the setup is very simple. Uh, Sorry about that. You have the water tank with the sloping bottom to represent the equator to poleward change in the height of the Taylor column. Or in other words, that is the beta effect you're representing by reducing the height of the water column. You're slowly releasing a dyed water here at the bottom to represent the deep water formation. So when deep water from the surface sinks and comes down to the bottom, it's going to be represented by this dyed water being released here at a rate of about 20 centimeter cube per minute, which is fairly low. And the tank is rotating at 5 RPM, which is also fairly slow. This is to set up a gentle flow so that you don't create random turbulent fluxes. Okay, what do we expect to happen? As we see, we are introducing the water here. Instead of the water just diffusing out in this rotating system with the homogeneous fluid with friction in the boundary layers, but interior flow basically being frictionless away from the boundary. The water actually flows west. Imagine that this is the Jinsee's way in the northeast of the North Atlantic, and deep water is forming somewhere there. It's not going to flow into the interior, it's going to flow to the western boundary and then come down south. And you can see that these are taken every 10-minute intervals. And as it comes down the western boundary current, it's sending off these zonal jets. What are they? Basically, remember the deep flow is uniform, the stratification is very low. So if we remember our potential vorticity or the Taylor column wanting to remain the same length parallel to the axis of rotation when you have steady flow, frictionless, homogeneous, steady flow, you get F over H to be basically constant because H doesn't change in this homogeneous fluid. So imagine the stratification being very weak and H being the height of, let's say, a density layer, which means F over H has to remain constant. So F has to remain constant. So when we looked at the F over H of deeper isopycnals, deeper sigmas, we had seen that they remained basically along latitude lines. So this is similar to that. We will see that even in the real world, when the deep water flows south in the western boundary, it sends off these zonal jets. They're observed, but not well enough to explain their scales, their time scales, depth scales, strengths, etc. Nonetheless, in this context, we can look at the volume flux S, which changes the height of the water column because you're adding water to the tank. So the height change of the water column over time has to be related to the flux of the water being introduced, which is 20 centimeter cube per second, divided by the area of the tank which is receiving this excess water. So S over L squared has to be related to the rate of change of the water level in the tank. And the W that is associated with that as well has to be delta H or delta T. You can think of this as the compensating rising flow in the interior to match for this mass flux going south. Okay, we will see that there will be northward flux being set up in the interior with rising flow at some mid depth, right? So that's delta H over delta T, which is just dH dt, S over L squared. And the meridional flow needed to compensate for this flow out as well has to be dz dy, and that is alpha. Basically, that is the change in the height of the water column. Okay, so you're going from deeper water column here near the equator to shallower water column here. So that height z is changing. So dz dy is basically the slope of the bottom alpha. So the w or v because W is dz dt and V is dy dt. The W over V is essentially alpha. So V, the meridional flow induced by this deepwater formation and its flow southward, is related to W over alpha, which is 1 over alpha S over L squared here. This is just to show you the scales that we have to worry about. We will apply this to the real world as well soon. So this is what is happening. You are introducing this deep water here in the shallow end, which represents the high latitudes. And that is going to raise the water level in the tank, which is going to induce the Taylor columns to try to adjust to this changing water level by moving northward to shallower end of the tank. So this is how the meridional circulation is introduced. As we said before, the sinking is happening in the north and the meridional flow is towards the north to compensate for this sinking as well. Remember the schematic by Henry Stommel as well. Okay, so that was the integral we had done before from bottom to the mid depth. V dz was F over beta W mid depth when we integrate F dW dz, because W is 0 at the bottom. There is no water coming out of the bottom. So upwelling basically happens by entraining water to basically stretch the Taylor column, which forces it to move northward. Okay, so this way the height of the Taylor columns are maintained and there is a northward flow introduced. We will relate that in some sense to how we thought about wind stress curl, Ekman pumping, and the Sverdrup circulation, the integrated meridional transport that we talked about. Remember, in the subtropical gyre, the wind stress curl is negative, so there is a southward flow, and in the subtropical gyre it's positive, and there is a northward flow, right? This is kind of what we will do in the next podcast. So I will leave it there and continue this in the next podcast. Make sure you understand the concept. These are very simple. Near the surface, there is wind forcing, which is creating Ekman pumping and trying to change the height of the water column or the Taylor column. And in response to that, Taylor columns have to move in the proper direction on the planet in the thin spherical shell to maintain their height parallel to the axis of rotation, because the Taylor columns cannot tilt over or they cannot get fatter, because then the angular momentum will increase and the assumption of steady flow will fail, as we saw in chapter 10, but they can change their height by moving on the planet, right? Then they can still satisfy Taylor-Proudman theorem in that sense, in the interior where friction can be ignored, okay? So we'll derive those equations and then show why there is a western boundary intensification. Near the surface, we said two things. We said the interior Sverdrup transport creates the gyres, and to match the circulation of the winds and to produce positive work done by the winds on the ocean, the boundary current has to be on the west. I also showed some simple example of how vorticity is being put into the ocean, and the balancing vorticity can only be generated on the western boundary and not on the eastern boundary. Now we have to do similar arguments without any winds, but just by the introduction of deep waters, and that introducing a western boundary current. Here, the western boundary current is forced to go south because heavy water is sinking and it is flowing south across along the western boundary. So there also the water column has to stretch, which means it has to acquire mass from somewhere. I'm explaining it kind of in words, but we'll see how that works out with equations, okay?